Welcome to my YouTube channel. And today's in this NLP series, we'll look into text representation. So, text representation means converting the text into numerical form. Basically, for machine learning models, we need the text to be converted into numerical form because the machine learning models are based on mathematics. So, to perform any kind of mathematical operations, you need the numerical data. So, text are converted to numerical form, and we'll look into the ways in which we can convert the text into numerical form. And there are various techniques. The first one is the frequency-based representations. So frequency means the number of count of each of the tokens. So we count the tokens, and based on the count of the tokens, we convert the text into numerical form. In this frequency-based representations, we have few techniques. Let's look into each of them. On the first one is bag of words. So it's as the name indicates, it's just a bag full of words. Okay, so we'll see how it's a bag of words and why it's called bag of word. So let's before we proceed, first we need to understand what are the terms used in the NLP. Uh, so let's suppose you are working on review classification. You have reviews for a product. Okay, you have reviews for multiple products, and you want to classify the review into different sentiments, positive and negative and neutral sentiments. Okay, so each of the review are different data points because you are you are processing each of the review. So each of them are different data points, and each of the reviews or each of the data points are called document. And a collection of documents or collection of reviews here will be called a corpus. So we have two terms, document and corpus. Corpus is the whole collection of the data points, and each of the data points are called document in NLP. Okay, so let's suppose we have these three sentences, okay, and we are trying to do some kind of classification task on this sentence. Okay, so each of the sentence are separate documents. So I have given D1, document 1, document 2, document 3. So we have these three sentences. And first we do tokenization as we saw in the last video. So in tokenization, we can use different kind of tokenization. Here we are using the word-based tokenization, which is the most common one in traditional NLP. So after converting to tokenized form, and we also have done the lower casing here. I have not shown any other things like stop word removal. But let's ignore that for now. We're just converting the text into lowercase and then we are tokenizing. So here, once we tokenize, which of the words will be separated? So document 1 will contain these words with 4 words, and then document 2 will contain these words. Okay. Once we have tokenized, we need to count the frequency. We need to get the frequency of each of the token. So here in this table, as you can see, we have 3 documents, and for each of them, we have calculated the token count. Uh, so the is occurring once only, dog is occurring once only, is 1, and for happy, the count is 1. In the second example, in the second document, you see the sentence is the child makes the dog happy. So the is occurring twice. So the for the we have 2, and for each of the other words, we have 1. Similarly, in the D3 as well, the is occurring twice. So we have 2 for the. So once we have done the counting of the words, once we have the frequency of each of the word, we can get our big word representation. So first we need to get the unique word in all of the document or the whole corpus. So we have this child, dog, happy, is, makes, the. So these are the unique words present in all of the corpus. So we first get them, we create a array of them, okay? And it's in alphabetical order. So we have created array of size 6 here because we have 6 different unique words in this whole corpus. And for document 1, we'll put the count of each of the token or each of the word in respective positions. Okay, so this is the dimension of the array, which is six uh, elements are present in this array, and vector representation will be also of 6 because we have 6 different unique words in this whole corpus. Okay, so let's fill this array. For D1, we have child is 0. Okay, dog is 1, happy is 1, is 1, max 0, and then the 1. And for D2, we have count for word child is 1, and the frequency for dog is 1, happy is also 1, is 0, and max count is 1, and the count is 2. And similarly, D3. So as you can see, if you put all of them together, right? If you put the first row, then we'll get the vector representation of D1. So this is the Bega word vector representation of D1. This is 0, 1, 1, 1, 0, 1. And then for D2, it's 1, 1, 1, 0, 1, 2. And each of the element in this vector or each of the element in this array are corresponding to one of the word, okay, which we can see from here. The first element in this vector is corresponding to child. It's counting the number of r- count for word child. And the second element in this vector is corresponding to dog. So this is a one way of representing the text into a numerical form. So let's look into the code for Vega words. So let's connect first. We need to import the count vectorizer, which is present in sklearn library in the feature extraction module. So we'll import the count vectorizer, which will be used for getting the Vega words. And we have these three documents or three sentences. Let's create the corpus here. And we need to initialize the count vectorizer and call the vector fit transform function or fit transform method from the count vectorizer. And there we'll pass the documents, all the documents. We'll get the Vega word. So let's run this and then let's run this. So basically here we have initialized, we have transformed our document into we have transformed our corpus into numerical representations. So after transforming the document into numerical form, after transforming the corpus into numerical form, what we are doing here is we are getting the feature names. Okay, the feature names are the unique words that we had. So we'll see the feature names. And the unique words are also called vocabulary for this corpus. And then we have the matrix that we saw. It will have the vector representation of each of the sentences, basically the Vega word representation. Let's run this. So vocabulary is child, dog, happy is mixed up. As we saw in the explanation, this is the vocabulary. And as you can see, this is the representation for the document 1, which is the dog is happy. So you see, for child we are having 0, for dog we are having 1, for happy here we are having 1, for is we are having 1, max we are having 0, and the is again 1. So this is similar to what we have seen in the explanation. So this is how the backward representation works. You can use the sklearn library for it. So this is the count version of the backward, and we also have the binary version of the backward. Basically, here what in binary version what we do is for 0 we have 0, and for any other number for some anything greater than 1 or equals to 1, we have 1. Okay, so if it just checks if the word is present in the sentence or not, it doesn't count. So if you run this, you'll see that we are having 0 1 1 1 0 1 and then 1 1 1 0 1 1. Here we are having 1 for the because we are not counting the word the, we are just checking if the is present in the sentence or not. Okay, so to get the count binary version of the backward or binary backward representation, what you do is you just pass this binary equals to true parameter in the count vectorizer. Then next we'll look into NGRAM and why it's useful. Before proceeding, let's see. Given this representation, let's see. Let's use this one. Given this representation for this and this vocabulary, it might be very difficult for us to understand the sentence that it produces. So given this, suppose you are only given like you're only given this. Let's make it slightly complex. Yes. It will be very difficult or slightly difficult based on the sentence to get back to the sentence from this representation. That means while converting the sentence into the vector representation, we're losing some information. Okay, so um, you can see here as well, right? For both the last sentences. Okay, so document 2 and document 3, uh, those are two different sentences. But for both of them, we are getting the same representation, same thing we are getting. That means we are losing some information while converting the text to uh, numerical form. And to reduce this loss of information while converting, we have this NGRAM. So basically, what happens in NGRAM is that let's look into this example to make it clear. Let's download this word tokenize to show. Okay. So we have this sentence. I tried to reset my password, but the reset link didn't work. We have tokenized it. We have tokenized this into a word-based tokenized form. Now we get the unigram. So unigrams are the simply the tokens only. So unigrams means one token. Uni means one, right? So unigram means one token. So this is just the tokens. Let's look into bigram to make things clearer. Bigrams means a combination of two tokens. Basically, uh, here I tried is occurring, right? So it will combine two tokens in sequence. It's not a random combination. It's based on the occurrence of the tokens in the sentence. Then try 2 is occurring here. Then 2 reset, you can see. Then reset by is occurring here. So it's just a combination of two tokens. I think it's very easy to understand. And then we have this trigram. As you can imagine, it's just a combination of three tokens. So I tried to reset my password. So as you can see, if you jumble this up, unigram, it will be very difficult for you to understand what was the sentence. And if you jumble this up, it will be slightly more easier than the unigram because we have a sequence of two words in bigram. Okay. In trigram, if you jumble this up, it will be much easier to understand or to get back to the original sentence from this trigram because we have lots of information present here. So we saw here, right? We are in bigger words, we are losing some information while converting to numerical form. So to reduce this loss of information, we can use a combination of unigram, bigram, or trigrams. Any of the combination can be used. So for easier explanation, I'm just using the bigram here. So to use the bigram, you need to give the NGRAM range parameter. So we have this NGRAM range parameter. In this parameter, you provide the range of NGRAMs to use. And in this, you need to provide the starting and end of the NGRAM. Okay, here we are saying the starting is 2 and end is 2. So that means it will only show the bigram. So let's just run the fit transform method. Then we'll convert this to vector form. Now our vocabulary is this: child happy, child makes, dog happy, dog dog makes, is happy, makes the child, the dog. Okay, so all the unique bigrams are present in this vocabulary. Okay, so now if you see, this is our vector representation of this of the first document, which is dog happy. Sorry, dog is happy and the dog. So we have dog is happy and the dog. So it's easier for us to understand this sentence will be the dog is happy. And for document 2 and document 3, you see that the representation are different now. Okay, earlier for when we are using unigram, the representation were same only, the vector were same. But here we are seeing two different vectors because they are using bigrams. If you see the last sentence, it was the dog makes the child happy. One means the child happy, okay? We are having the child happy, and then we are having dog makes the child the dog. If you are given this representation in this vocabulary, it will be easier for you to understand the sentence or get back to the sentence from this representation. So that means we are losing less information as compared to the unigram. And if you use trigram, then you will have much more or less loss of informations. And let's show you. Let me show you. So how people uses it. People will just use like unigram diagram or unigram diagram trigram based on the need of the project. So if you use 1 and 2, sorry, 1 comma 2, then that means both unigram and bigram will be shown here. So now the vocabulary will contain both the unigrams as well as the bigrams, come sequence of two. Okay. If you want to use all the 3 grams, you can use 1 comma 3. So it will use 1, 2, and 3 grams. See, okay, so let me just use the bigram and show you one thing. Now you see, when we are using the bigram, the the length of the vector is increasing. The size of the vector is increasing. So if we are using the unigram, we had length of 6. Okay. Now it's 9. Okay. And if you use trigram, it's 10. Okay. So as you can see, when we are using we're going from unigram to bigram, from bigram to trigram, the length of the vector is increasing. The dimension of the vector to represent the sentence, to represent the document is increasing. And if you use a combination of like bigram, trigram, then the length will be much more. And here we are using a very simple example, so it's manageable for us. But what happens is that if you are using this in a real project, it will go to tens of thousands, which will make the model very difficult to understand. Okay, so you can't just use all the grams. You can think like if I'm using all the grams, or if I'm using like 4 gram, 3 grams, then we'll not lose any information. But the problem will occur there is that you will have lots of dimensions, and which will be a problematic. Once you have lots of dimension to work with, the model will not be able to understand clearly. The model will have hard time to process the data. We'll face the problem of curse of dimensionality. So here you can see the curse of dimensionality refers to the various phenomenon that arises when analyzing or modeling a data with many features or high dimensions, where the data becomes increasingly sparse and difficult to interpret or model. So this is an issue. Our data will become very sparse, right? You can see here our data is very sparse. We are only having few places we are having one, all are zero. So this curse of dimensionality problem will come into picture. So let's look into uh, count vectorizer on sklearn. So this is coming from sklearn. Let's look into the documentation of count vectorizer to understand more. So in the documentation page of the count vectorizer, we will see the various parameters the model have. So we have the input, we have encoding and decode error. So then the strip accent, lowercase. Okay, by default is true. What it will do is it will convert all the characters to lowercase before tokenizing. So here you can see in the count vectorizer, we are not tokenizing and then passing the token to the count vectorizer. We are just passing the whole corpus to the count vectorizer because internally it will tokenize. Okay, so it has internal mechanism to tokenize the sentences. And you can see this is the tokenizer. You can also create your own tokenizer. By default, it's none. None means it will use the word-based tokenizer. Okay. So then you'll also have the preprocessor parameter. If you want to do some kind of pre-processing, you can create a function and then use that preprocessor parameter. Then we have stop words. By default, it's none. And then token pattern. Basically, this is used for tokenizing. And by default, it's using this token pattern, which is to tokenize based on word. We have the NGRAM range, min max. Okay. With the NGRAM range, which we saw. And then let's look into max DF and min DF. Max DF is maximum document frequency. So when building the vocabulary, ignore the terms that have document frequency is strictly higher than the given threshold. Okay. So while creating the vocabulary, counts for each of the word, each of the token, it will count the frequency. If the frequency is higher than the given uh, max TF parameter, then it will be ignored. If it is a count, then it will be count will be used. If it is a float, a decimal number, then the percentage will be used. So if float the parameter represents a proportion of the document's integer absolute counts. So let's look into this with an example. So let's suppose we are saying the max TF is 2. Okay, the max TF is 2. So all the tokens which are occurring in more than 2 documents will be ignored. So the is occurring in 3 documents here, right? The is occurring here. In this document is also occurring. In this document is also occurring. Happy is again occurring in 2 documents. Sorry, 3 documents. In all the 3 documents is occurring. We are just counting the occurrence of the word or token in number of documents. In how many documents is occurring. So let's run this to see. Now as you can see, the vocabulary now is child is max. We are not having the because it's occurring in all the 3 documents, and we have mentioned like we want only to have max TF 2, right? So we have mentioned max TF 2, so the will not occur. Happy is not occurring, and dog is also not occurring because dog is also present in all 3 documents. And then we have the min DF. So next thing is the min DF or minimum document frequency. So you can see the explanation here. Okay. When building the vocabulary, ignore the terms that have a document frequency strictly lower than the given threshold. So if the term is having document frequency lower than the given threshold, then it will be ignored. It's also called cutoff in the literature. And similar to a max tier, we can have floating number and or integer number. So let's see if we have any unique words. So as you can see, in this corpus, the is occurring only once. Okay, it's only occurring in one document. Only in the first document we are having is. In other documents we are not having is. So if you mention that min df is 1, then is will be ignored from the vocabulary. Let's run this. Sorry, it should be 2 because anything lower than, don't think it's lower than or equals to, it's I think strictly lower than. So strictly lower means it's lower than, it's not lower than or equals to. So we should be using 2. By default it's 1. By default it's 1. So anything lower than 2, so we should be using 2. Once we use 2, we'll see that the is ignored and it's not in the vocabulary. So these 2 terms, max df and min df, are used to regulate the dimension of the vector. Okay. So basically, the idea behind min df is that in a document or in lots of, like if you are having lots of reviews. So if you are having lots of reviews, you might have some mistyping, right? So someone might type happy in this way, HAPY. Okay. But this is not a word. This is just a mistyping. So to reduce the mistyping errors or to remove the mistypings, we can set the main df to a higher number like 2. Here you can set 2, right? So this will get rid of this mistyping, right? And idea in the max df is that some word might occur in all the documents, like the is occurring in all the documents or most of the document. And if it is occurring in most of the document, then it might not be very useful. It might be just a word which is everywhere, so which is present everywhere. So it's not having any kind of significant information. Okay, and let's look into other parameters. We have max features. So we can cap the number of features or cap the dimension, and we can also provide vocabulary. So we can so here it's the vocabulary is created based on the examples given here, right? It's created on its own. We can create our own vocabulary and we can provide that using this parameter. And then the model will not create any vocabulary. It will use the given vocabulary. And based on the vocabulary, the vector representation will be created. And the binary flag or binary parameter we have already seen. So these are the various parameters we have in the count vectorizer. The next text representation, which is based on frequency, is TF-IDF. The full form is term frequency, inverse document frequency. So it's comprised of two terms, term frequency and uh, in IDF. So it's an extension of BoW words. So you can it's calculated from the BoW words representation only. It's slightly more complex than the BoW word representation. So let's look into this formula. So we have this formula TF-IDF. We are having three terms in TF-IDF. The small d is the document, the capital D is corpus, T is the term. Term means the token or the word. So this is the parameters in TF-IDF. So we are having term frequency, which is calculated per document, and then the inverse document frequency, which is calculated per corpus. Okay, so the formula for term frequency is number of times term T appears in the document D divided by total number of terms in document D. In the IDF is total number of documents divided by 1 plus number of documents containing the term T, and we take log of this. So let's look into example to make this clearer. So we had this example of three sentences or three documents, which we saw in the BoW words. So we are having this BoW word representation of the three documents, and from this only we'll be able to calculate the term frequency. Basically, the term frequency is divide the each of the element in the vector by total sum of that vector. So 0. So how many? What is the sum of this vector d1? The sum is 4, and for d2 it's 6, and similarly for d3 it's 6. So in d1, what we will do is we'll divide each of the element in the BoW word by 4. So 0 divided by 4, 1 divided by 4, that p is 1. So we divide it by 4 and is divided by 4. We are taking sum of this d1 and dividing each of the element in d1 by sum. Similarly for d2, we take the sum of the d2 and divide each of the element in d2 by the sum. So this is the term frequency. Okay, so we have two terms, term frequency and then the IDF. And then the IDF or the inverse document frequency is calculated by counting the number of documents and number of documents containing the term T. So the number of documents will remain same, and for each of the term you'll have to calculate the IDF. So for the term child, it's occurring in two documents. Okay, for the child, you see it's occurring in D2 and D3. Both document 2 and document 3 is occurring. So doc count is 2 for child, and then for dog, The document count is 3. So the dog is occurring in 3 documents. Similarly, happy is occurring in 3 documents. Is occurring in 1 document. So dog count is 1 here. Max is occurring in 2 documents. The is occurring in 3 documents. We are not taking the sum here. We're just checking in how many documents the term is appearing. So we see that dog is appearing in all the 3 documents. The dog count for the is 3. And we apply this formula log total number of documents. So we had 3 documents divide by 1 plus dog count. 1 plus dog count, that means 1 plus 2 is 3. Okay. Similarly, for this term, we'll have this IDF. Now that the term frequency is calculated and the IDF or inverse document frequency is calculated, we can multiply both the term. So TF-IDF is term frequency multiplied by inverse document frequency. So we have this here. We can multiply both these terms to get the TF-IDF representation. Okay, so this is the TF-IDF representation of these documents. And you can see here for D1 we are having 0.00, and then 0 minus 0.31 and so on. So this is the TF-IDF representation. In the TF-IDF representation, we'll have floating point numbers because uh, we are dividing and then we are also taking logs. So we'll have floating point numbers. So TF-IDF gives more importance to the words that appears frequently within a document. So if the word is occurring very frequently within a document, within a within a data point, then it will be given more importance. And IDF gives more importance to the words that are rare across the entire document. Okay, so it gives the importance to the words which are occurring very rarely in the whole corpus. So let's look into the code. So similar to the beggar word, we have TF-IDF vectorizer in sklearn. We can import it, and similar to the syntax is similar to the count vectorizer. We are initializing the TF-IDF vectorizer, and then we are transforming the our documents. So we had the same documents. Let me just print the document as well. We have this 3 corpus. We have the same corpus, okay, where we are having 3 documents, and we are transforming them, and we are getting the matrix. Okay. You may think that you may see that we are having the numbers slightly different from what we saw in the explanation. That's because the internal uh, internal formula used in the sklearn library are slightly complex than what we saw, but the core idea remains same. You can see similar to the Bego word, we are having this vocabulary, and then we are having this for each of the document. We are having these three different vectors for each of the documents, and each of them are vector representation of each of the respective documents. So let's look into the document of TF-IDF vectorizer. So similar to count vectorizer, we'll have documentation of TF-IDF vectorizer. So this is the documentation on sklearn on the TF-IDF vectorizer. The parameters will be similar to what we have seen in the count vectorizer. So all of these parameters we have already seen in the count vectorizer. See, we have this term. Let's look into one of the term which is very important. Use IDF. By default, it's true, but you can set it to false as well. Basically, if you're not using IDF, only the term frequency will be given. So let's see that in action. So let's say use IDF so false. Now we will only see the term frequency. Yeah, the numbers won't be what we expected because the actual calculations happening in the library is slightly different. But as I mentioned, the core idea is same. So this is one another frequency-based text representation that we can use. And since it contains other information as well, so the bigger word and the bigger word contains only the counts, but the TF-IDF contains more information than bigger words. Thanks for watching.